Good afternoon.
Good afternoon.
All right, so is anybody in St. John's?
We're missing David.
Okay. All right. Thank you. And thank you for adjusting that camera. Okay, so today we are going to finish 7.3 and maybe start in on 7.4. I'm not sure how far we'll get there. So, but any questions, comments, concerns before we get started on today's? All right. Okay. So this first little bit of notes here is actually not on the it's not on the sheet, because this is actually just a review of the general power rule for derivatives. So this is actually back in Calc 1. I just wanted to kind of remind you of the power rule, so you can write it down or not, but. Remember when we had a variable raised to a power, okay? Then what you did to take the derivative is you bring the exponent in front and then lower the power by 1. So that's what we call the power rule. Now, what we're going to find out today is that only works when the exponent is a number, okay? When it's a variable, then we got to do something else. Okay. So this is the one that we're going to do, is that, see if we have x to the x power. All right. So the first thing we're going to do, and this is the blank there, is that we want to rewrite x to the x as e to the x natural log x. So we're just kind of rewriting it a little bit. Now, this example 5 that I go through, it's actually also practice 5. So because I want you to have this exact problem in your notes and to go through, so I want you to go ahead and take notes on this problem on practice 5. Okay. So. Because the reason why you can get away with this is because, remember, e to the natural log of x just becomes x. The e and the ln sort of cancel. So you would end up with x to the x. Okay? Now, suppose we want to find the derivative of this. Okay? Well, so what we do is we think of the a to the u formula. Okay, so the a to the u formula says that the derivative of a to the u is a to the u, so the exact same thing you started with, times the natural log of the base, so times the natural log of e, times the derivative of the exponent. And so that we need to take the derivative of. And so I've just kind of got here that in order to take the derivative of that, we're going to have to use the product rule. Okay, so we've still got some more work to do. All right, so to do the derivative of that, the product rule, we take the first x times the derivative of natural log of x, which is 1 over x, plus the derivative of x, which is 1, times the second, which is natural log of x. Now, so cleaning this other part up, e to the x natural log of x, now I'm going to actually turn that back into x to the x, because the e and the ln will cancel, bringing us the x down. And then natural log of e, that's just 1. So that's why that's not up there. And then if I clean this part up in parentheses, the x's cancel, so I get 1 plus natural log of x. So I've highlighted it because this is the final answer here. So the derivative of x to the x is x to the x times 1 plus the natural log of x. And so I don't know why, but a lot of calculus finals, the AP exam, so on, will have this exact problem on it. Okay, I've seen it so many times. I just decided we're gonna work it through in class. Okay, so I'm not saying you actually have to be able to go through this, although it wouldn't be bad, but you definitely want the result. Okay. All right. Any questions on that? Okay. All right. Now the other thing with E is we kind of defined it as the inverse of the natural log function. There's another way that E can be defined as a limit. And so this will actually come up later again, but you can express E as a limit as x approaches 0 of 1 plus x to the 1 over x. Now, it's kind of weird because you might say, well, 1 plus 0, that would give me, if you plugged in 0, you'd get 1. 1 over 0 would approach infinity. So 1 to the infinity, what would that be? Well, if it was exactly 1, it would be 1. Because 1 times itself, however many times, would be 1. The problem is if it's 0.9999999 to the infinity, see, any number less than 1 raised to the infinity power would go to what? So let's say like a half. If you kept multiplying a half by itself, what would it go to?
It would get to 0, right?
It would go to 0. Okay, but then if you took a number slightly more than 1, so like 1.001, and raised that to the infinity power, then what would that be?
You'd eventually get to infinity.
It'd eventually get to infinity. So it's like you have a tug of war right there at 1. One side goes to 0, the other side goes to infinity. So we're going to learn how to deal with limits like that, okay? But for now, just know that this particular limit actually goes to E. And we'll prove that at one point. Okay? All right. Okay, so the derivative of e to the u was e to the u times the derivative of u. Okay, so we did that before. All right, so now what we're going to do is say, well, what if e is a different base? What if the base is something other than e? Okay, so I actually used this in the previous problem. The derivative of a to the u is a to the u times the natural log of a times the derivative of u. So in red here, I've kind of applied this to where we did the derivative of e to the x was e to the x. Well, you could actually still use this formula for e to the x because the derivative of e to the x would be e to the x times the natural log of e times the derivative of x. Well, the natural log of e is 1, the derivative of x is 1, so you just end up with e to the x. This is the integral equivalent. So the integral of a to the u du is a to the u divided by the natural log of a plus c. So with the derivative, you multiply by the natural log of the base. For the integral, you divide by the natural log of the base. So again, the integral of e to the u du, you could say, well, that's going to be e to the u divided by the natural log of the base plus c. Well, the natural log of e is 1, so you just get e to the u. But so these two are very important when your base, see, when we have the power rule, that's when you have like x to the 5th power and you want to take the derivative. So if you switch those numbers and instead of x to the 5th, if you have 5 to the x, then this is how you take the derivative of that, or the integral of that. So when the number is the base and the variable or function is the exponent, then these are the formulas that you use. Okay? Now, it's funny because like I actually at my morning class, they started like January 6th, so they're several sections ahead of you guys, and we have to keep referring back to these formulas because they're forgetting. They're like, how do you take the derivative of 2 to the x? I'm like that. This is the formula. Okay? Because they know the power rule doesn't work. Okay? So, all right, so let's look at well, let's do 2 to the x. So let's say y equals 2 to the x. So then y prime, so you say that bring down the same exact thing, 2 to the x times the natural log of the base. So times the natural log of 2, and then times the derivative of the exponent. So times 1. And really that's it. I mean, you could not write the 1 if you wanted, but I would probably write this as 2 to the x times the natural log of 2. And that's it. That's the derivative. Okay? So let's see if we had, let's see, find y prime. Okay, so let's look on this one. So the derivative, well, let's let you go ahead and do those. So do A, B, and C. All right, so Hannah, I choose you for A.
All right, I got 4 to the x times the natural log of 4.
That's it. Well, maybe that's it. Okay, we're frozen. Let's see if I can work here from the computer. Okay, good. All right, Joey, how about the second one?
I got -4 to the x ln of 4.
Okay, so it's still going to be to the negative x.
Yeah.
Okay. All right. Any questions on that one?
Can the negative go anywhere?
Can the negative go the negative in front of the 4?
Yeah,
but
does it?
if you put it in front of the ln, you'd have to put that in parentheses.
Okay.
Okay. All right. So Hannah, I guess you get to do C as well.
I got negative sine x times 4 to the cosine x power times natural log of 4.
That's it. So, really, if you have a negative, usually that term I write first, just so it doesn't look like subtraction. And then I think you said this one before, the ln of 4. It doesn't really matter. Although some people would say, well, this is actually a constant. This is a number, so put it in front of the trig function. But it doesn't, it's all the same. Okay? All right, any questions on that? All right, good. Okay. All right, so now let's do, so if we had the integral, let's see if this is going to work for me. So if we had the integral, no. Okay, so let's see if it'll, no. So if we had the integral of 2 to the x dx, then you say, well, that's going to be 2 to the x, and then it's divided by the natural log of 2, and then your plus c at the end. Okay? Now, if whatever this exponent is, if you don't have its derivative, well, then you've got, like, let's say it was 2 to the 3x or something, then you would need a 3 right here. And so you'd multiply by 1/3 in front. That little trick that we did before. Okay? So let's just see how you do on those last couple for practice 6. All right, so David, when you've got D.
So is it 3 to the x power over the natural log of 3 plus c?
Yep, that's it. All right, any questions? All right. All right, so Chloe, when you get this one, or if you get stuck, let me know. I will give you a hint. I would do this one by U substitution.
I'm not totally sure, but I'm pretty sure it's negative 3 cosine x over ln 3. And I don't know if there's supposed to be sine x or not, and then plus c.
Okay, so first of all, if you think of the so I think this is what you said, right? Right, Chloe? Isn't this what you said?
Yes.
Yeah, so that's correct.
Oh, okay.
So let's just go through it. So if you do your U substitution, so let U be cosine x, and du is negative sine x dx. Then this becomes 3 to the u, but in order to get the du, you need a negative here. So you put a negative in front of the sine x. So now that's going to be your du. But to compensate for that, you've got to put a negative in front. Okay? So that gives you negative 3 to the u, and then the negative sine x dx. All of that is going to be your du. So all of this is your du, and then this is your 3 to the u. But you have to have the negative there to make it work. And so then you integrate 3 to the u du is, still have the negative, then it's 3 to the u over the natural log of 3 plus c, and then you substitute back what u was, which is cosine x. So then this will be your final answer here. Okay? All right, any questions on that one? All right. Okay, let's see. Oh, I've got this. Okay, so now the derivatives and integrals of the log. Oh, I'm forgot. I'm not the camera. Okay, so here's a couple of equations for logarithms. Okay, so a raised to the log base a of x is x. Log base a of a to the x is x. So we actually did those back in 7.2. Okay, then here's the change of base formula. Okay, and then this is the derivative. Remember, the derivative of the natural log is like the derivative of the natural log of x is just 1 over the natural log of x. So this is the general form of the derivative of log base a of u, or log base a of x. So it's 1 over the natural log of a times 1 over u times du dx. So if I had the derivative of here, I'm going to rewrite this last part. Okay, so if I applied, okay, if I applied the derivative of the natural log of x, okay, so that would be, so the natural log is log base e. So you'd have 1 over the natural log of e. So 1 divided by the natural log of e. So that would be the first product. Let's see. Let's do times. It's kind of hard to do on a keyboard. Times. So then you'd have 1 over the base, 1 over x times the derivative. So the derivative of e to the x, which would be e to the x. Okay, so the natural log of e is just 1. So this first part would just give us 1. And then we have times 1 over x. Oh, I'm sorry, it's times the derivative of x. It's times dx dx. 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 Okay, so we'd have 1 times 1 over x. This type in this is really butchering this. I'm sorry. So 1 divided by x, and then times 1. And so then all of that would just give us 1 over x. So the derivative of the natural log of x is just 1 over x. So that's sort of a specialized rule. But in general, we can use this to take the derivative of not just the natural log, but log base anything. Okay, so it's 1 over the natural log of the base times 1 over the function, which we are used to with natural log, and then times the derivative of that. Okay, so the last two parts are kind of the same. All right, so I know I've kind of butchered that a little bit, but let's do some examples here. So let's say if we wanted to do the derivative of log base 10 of 3x plus 1. Okay, so applying that formula, it's 1 over the natural log of the base, which is 10, times 1 over 3x plus 1 times the derivative of 3x plus 1, which is 3. And that's it. You just kind of write it together. There's really no simplifying you can do or anything like that. Okay? All right, so do practice 7a. All right, so Joey, what do you have?
Okay, so I got 6 over the natural log of 10 times 6x plus 1.
Very good. So I was happy that you said the natural log of 10, because some people forget that, because that's a common log, so the base of 10 is understood. Okay, so good job on that. Any questions on that? Okay, so now let's go back to the integral formula. Okay, let's see, where is the integral formula? Okay, so so I guess to do the integral here, what we're going to do is rewrite, when we have a different base, we're going to use the change of base formula to write it as a natural log. So the log base 2 of x, using the change of base formula, that's the natural log of x divided by the natural log of 2. Okay, and then we still have x in the denominator. So putting the x with the natural log of 2, we can make it so it's not a complex fraction, and just write the natural log of x. Oh, we still have a dx though. Okay. All right, so now when you see that natural log of x over x, that's actually, we can do a u substitution on that, because if we pick u to be the natural log of x, see, the du is going to be 1 over x. So this is the du down here, 1 over x dx. So you might say, well, what do I do with the natural log of 2? Well, that's a constant, so you can actually pull that out in front. So bring the 1 over natural log of 2 out in front, and then you have natural log of x over x. So that's u, and then the rest of this is du. And so now the integral of u du, you add 1 to the exponent and divide by that. And so, and then make their u substitution back, substitute back in terms of x. So we're going to get natural log of x squared over 2 times 1 over natural log of 2 plus c. And here I just combine these together, but that's about it. All right, so using this as a model, I'll leave this up here. See if you can do practice 7b. Oh, before I forget, St. John's, when did you guys want your quiz for tomorrow? What time works for you guys?
I'm gonna be gone tomorrow, so could I do mine from 10:50 to 11:50?
Sure.
And then me and David want it from 250 to 350. Or no, wait, from 150 to 250. Yeah.
Okay. All right. Okay. So Joey and Damon at 150 and Aiden at 1050.
Yeah, correct.
And then we're also so Winslow at 150, Mogyan at 10, but Hannah is not going to be here tomorrow, and she wants hers on Thursday. Is that right?
Wait, I'm also not going to be here too. So Hannah and I both want ours on Thursday.
What? Sorry, I'm only doing that for Hannah.
Oh, I'll just do it
No, just
outside
kidding.
of.
I'll take care of you. So Thursday at 10 o'clock. Okay? All right. That sounds fine. And so I'm actually thinking about, okay, so I don't want to get backed up, but I'm a little nervous with having the two quizzes for the first time, and I'm trying to decide if I want to give you 7-1 and 7-2 or just 7-1 this week.
We should just do both.
Just do both, knock them
Yeah.
out? Okay, so here, let's make this deal. Let's set them up both. But remember, let's say, especially like on 7-2, if on the second attempt you don't have time, don't start it. Okay? So don't start it if you're not going to have time to finish it, and then we'll reopen it for you later. Okay? I think you should be able to do it but anyway. I hate comparing students, but I think you shouldn't have any trouble. But if you do, just don't start it, and we'll figure it out. Okay, so practice 7B. Let's see who's got this one. Aiden.
I got ln of x quantity squared over 2 ln 3 plus c.
That's it. So I actually like how you said it better because you combined those two. Okay, I can't write it. But ln of x quantity squared and then over 2 ln 3. So he put those together and then plus c. So perfect. All right, any questions? Anybody need me to go through that?
Yeah, could you go through that, please, real quick?
Okay, so first the log base 3 of x. You want to use the change of base to rewrite that as the natural log of x over the natural log of 3. Okay, so we're good with that. Okay, all right. Now, the 1 over natural log of 3, because that's a number, that's a constant, we're actually going to pull that in front and just make it natural log of x over x. And so then, just like the, just like the practice problem, see this, if this is your u, then see 1 over x dx, all this is your du. Okay, because the derivative of natural log of x is 1 over x dx. Okay, so if that's your u, so we actually have it written over here. So if u is natural log of x, then du is 1 over x dx. So then this just becomes the integral of u du. And so now we can use the anti-power rule and add 1 to the power and then divide by that new power and then substitute back what natural log of x was. Okay? Any questions on that? Any other questions? Okay. Well, let's, so that's it for 7.3. I'm going to give you just a little bit. I know we have only about 10 minutes, but I want to give you a little intro into 7.4 because it's actually a big section. And it actually kind of bothers me, 7.4, because in the previous edition of the book, this was 2 separate sections, and I liked it that way. Okay? And anyway, so I'm going to follow the book, but I really believe that it would be better if exponential change was taught separate than separable differential equation. The reason they put them together is because the exponential change formula that we use is we derive it from separable differential equations. So, okay. What you might remember, like in pre-calculus, you do problems like bacteria growth or population growth or whatever, and they give you this equation here. This equation for exponential growth is the one that we're going to use, and it actually comes from what's called separable differential equations. Okay, so what's that? Well, we'll talk about that in just a minute, but I want to give you some examples of exponential change, things that change exponentially. The problem with us as humans is we tend to often think that everything is linear, okay? And like if you, work $5, if you work 5 hours and you get $50, then if you work 10 hours, you get $100. See, that's linear. Okay, that's linear thinking. But see, something like population doesn't grow that way. Okay, and in like bacteria or something like that, the population may double. I mean, boy, it'd be nice if your money always did, but there are things that grow exponentially. You might remember doing problems either in pre-calculus or in science class about radioactive decay, where you're determining how much of the substance is left after a certain amount of time, or carbon dating, or all that kind of stuff. So that's another example. Rate of cooling. If you want to know, they take something out of the oven, how long is it going to take to cool? Or the rate of heating. Have any of you ever tried to cook frozen meat? It's a bad idea. You want to have your meat thawed, because otherwise it changes the consistency of it. And so for restaurants or whatever that keep their meat frozen, they'll actually have a chart that'll let them know, okay, so if you're bringing it out of the freezer, this is how long you need to keep it out to thaw it. So these are just some other examples. Can any of you think of anything else in the real world that changes exponentially and not linearly?
Interest.
Yeah, interest with money, because you're making or paying interest on the interest. And so it starts to grow. So if you can keep an investment, it really, that's when it starts paying off, is when it starts making money off of the interest that you've already made. Anything else? Okay, so a couple of them, students said that, somebody said that they actually saw that talked about word usage in a book, that some authors, as they continue on, will use the same words over and over again. And I thought that was an interesting idea, that their word use of certain words is exponential. Medication. Now, you might not know this, but as medicines build up or decay in your bloodstream, okay, if you take another dose, or like if you take, there's certain things, like let's say if you smoke marijuana, and then you have to have a blood test. Did you know that it's actually there's always traces of it. There's like trace elements of it for years later. So if they refine the tests, anyway, that's another thing. The different medications, hunger levels, light intensity, echoes, stress levels in high school, velocity due to gravity, war production, erosion, and then I thought this was good, a viral video. Because you post a video, that's what it means when say something goes viral, is that as you know more and more people are watching it, it grows exponentially, the number of views. And so all of these we can analyze using calculus and the formula that we're given. So if you think of any other ones by tomorrow, let me know. Okay? So the idea is that we look at this rate of change. So dy dt, we say that rate of change is a constant times y. Okay? So when we say that something is growing, then at a certain rate. Okay? And so we can actually go through here, and here I'm solving for y, and then what I actually do is integrate both sides. You might remember when we did this, the differentiation with logarithms. So this is what's called separable differential equations, where if you have two variables, you put, and I'm going to talk about this more tomorrow when we actually do it, but what I'm trying to tell you is that once you separate the variables and then you integrate both sides, and then you, as you manipulate it algebraically, what you end up with is that formula. So this formula that we have in pre-calculus is actually comes from calculus. It's just we don't derive it, or we don't tell pre-calculus people they're doing calculus problems. Okay? And so this is kind of the pre-calculus version, but this is what we use in calculus. This is what the formula that I'm going to work with starting tomorrow or Monday is saying that the amount of stuff at any time is equal to the initial amount times e to the kt, where k is that constant of variation and then t is time. Okay? So instead of using a, we use y sub 0 for the initial amount. Okay? So that's sort of the preamble. There's really, I haven't given you any notes or anything yet for 7.4. So we're going to start with that tomorrow. Okay? All right. So thanks you guys for today. Any questions or comments before we pack up? All right. Well, we'll see you guys tomorrow.